Ever wondered how common medications, maybe ones you've even used for stomach issues, like the original Tagamet or Zantac or Pepcid, how they actually work their magic?
Or even some really potent natural compounds. It turns out many of these crucial molecules, both synthetic and natural, they owe their activity to one specific type of compound, amines.
And that's exactly what we're diving into today on the deep dive.
Right. You've given us this really comprehensive chapter from David Klein's Organic Chemistry, and our job really is to cut through all the detail, pull out the most important concepts, the key mechanisms, the reactions.
And kind of define things simply, point out maybe some problem-solving tricks, even flag common pitfalls students run into.
Exactly. We want to make this fascinating world of amines understandable and highlight why they're such a cornerstone, not just in organic chemistry, but, in medicine and biology too.
Okay, so what should people expect? We'll explore what amines actually are, how they're classified, their unique properties.
How we make them, the reactions they undergo, and importantly, how chemists use all this knowledge to build complex molecules, including those life-saving drugs.
Sounds good. So let's start at the beginning. What defines an aminin?
Well, at its core, an amine is an organic derivative of ammonia, NH3. Basically, you take ammonia and you swap out one, two, or even all three hydrogen atoms with alkyl or aryl groups. Those are carbon-containing groups.
Okay, and that leads to how we classify them, right? Primary, secondary, tertiary.
Precisely. And this is a really crucial point. The classification 1 degree, 2 degrees, or 3 degrees depends on how many carbon groups are attached directly to the nitrogen atom.
Ah, right. That's different from how we classify alcohols, isn't it? With alcohols, we look at the carbon attached to the OH group.
Exactly. It's a common point of confusion. But for amines, it's all about what's directly bonded to that nitrogen. Getting this right is fundamental because it directly impacts reactivity, hydrogen bonding, physical properties, everything, really.
And these aren't just lab chemicals. Amines are everywhere in nature.
Oh, absolutely. Many alkaloids, which are these naturally occurring amines from plants, often have really potent physiological effects. Think about things like morphine.
The painkiller.
Right. Or cocaine, a stimulant, or nicotine.
Highly addictive.
Yeah. And they play vital roles in our own bodies, too, especially in neurochemistry. Dopamine, for example, crucial for motor skills and emotions. That's an amine.
And things like adrenaline and noradrenaline, our fight-or-flight hormones.
Those too,
Oh.
all amines. So it's really no surprise that so many pharmaceuticals incorporate an amine structure. It's a common effective feature.
What makes them so versatile chemically?
It really boils down to one key feature, that nitrogen atom has a lone pair of electrons. This single characteristic dictates almost all their chemistry.
Okay.
That lone pair allows amines to act in two main ways. They can act as a base, meaning they readily accept a proton, H plus CAD.
Like ammonia itself.
Exactly.
Oh.
Or they can act as a nucleophile, donating that electron pair to form a new bond with something electron deficient. Base or nucleophile, that's the core of their reactivity.
You mentioned drugs, and that brings up metabolism. Our bodies have to process these things, right? Turn them into something water-soluble so we can get rid of them.
Right. Drug metabolism studies are essential, and sometimes it's not even the drug you swallow that does the work, but one of its metabolites.
Yeah.
There's a classic example with the antihistamine terfenadine.
Oh, Seldane. I remember that.
Yeah, Seldane. It was a great non-sedating antihistamine, but it turned out it could cause serious heart problems if you took it with certain other drugs.
Why was that?
Well, those other drugs inhibited its metabolism. So terfenadine itself built up to dangerous levels in the body.
Uh-oh.
So medicinal chemists dug into it. They found that the actual active antihistamine was one of terfenadine's metabolites, a compound called fexofenadine.
How is it different?
The key difference was that fexofenadine had a carboxylic acid group instead of a methyl group that terfenadine had. This made it much more water-soluble and safer. It didn't accumulate dangerously.
Fexofenadine became...
Allegra. Seldane was pulled from the market, and Allegra became the safer, equally effective alternative. It's a brilliant, real-world example of how understanding metabolism leads to better, safer drugs.
Okay, so if we're going to work with these compounds, we need to be able to name them precisely. How does that work?
Right. Nomenclature. It can seem a bit daunting, but the goal is clarity. For simple primary amines, where just one carbon group is attached to the nitrogen, you often just name the alkyl group followed by amine, like ethylamine or isopropylamine.
Simple enough. What about more complex ones?
If the alkyl group is more complex, or if there's another functional group with higher priority,
Mm-hmm.
we treat the amine as a substituent. We name the parent chain like an alkane, but use the suffix adenine, and we number the chain to give the nitrogen the lowest possible number, similar to alcohols. So you might have, say, 2-pentanamine.
And what if the amine group isn't the main event, like in, say, 4-aminobutanol?
Exactly. If another group, like an alcohol, has higher priority, the amine is named as an amino substituent. And for aromatic amines, they're typically named as derivatives of the simplest one, which is aniline. So you could have metachloroaniline, for example.
Okay, what about secondary and tertiary amines with 2 or 3 groups on the nitrogen?
If the groups are simple and identical, you just use prefixes like like diethylamine or trimethylamine.
Easy. But if the groups are different or complex,
Then you identify the most complex alkyl group as the parent, alkanamine. The other, simpler groups attached to the nitrogen are designated using N, followed by the alkyl group name.
the N tells you it's attached directly to the nitrogen, not somewhere on the main carbon chain.
Precisely. So you might have something like N-ethyl N-methyl-2-hexanamine. The N tells you the ethyl and methyl are on the nitrogen, and the 2 tells you the amamine group is attached at carbon 2 of the hexane chain. It ensures everyone knows exactly what molecule is being discussed.
There's a skill builder in the chapter 22.1 that walks through this naming process step by step. Seems helpful.
It really is. Identify the groups, decide on the parent name style, assign numbers, put it all together. And speaking of names, there's a fun, maybe slightly morbid fact.
Oh.
Compounds like putrescine and cadaverine, their names kind of give it away. They're diamines, and they contribute significantly to the characteristic unpleasant odor of decomposition.
Right, the smell that cadaver dogs are trained to find. Amines again.
Amines again.
Okay, let's move beyond names to properties. What's interesting about their shape or geometry?
Well, the nitrogen in most amines is sp3 hybridized, similar to carbon and methane, but because of the lone pair, the geometry around the nitrogen is trigonal pyramidal, like a pyramid with nitrogen at the top.
And if you have 3 different groups attached to that nitrogen, it should be chiral, right? Like a carbon with 4 different groups?
Logically, yes,
Yes.
it is chiral. But here's the fascinating part.
Yeah.
At room temperature, these chiral amines usually aren't optically active. You can't separate the enantiomers easily.
Why not?
It's due to a phenomenon called pyramidal inversion. The nitrogen atom rapidly flips its configuration, passing through a planar transition state. It's like an umbrella turning inside out in the wind, happening incredibly fast.
Wow.
The energy barrier for this inversion is really low, only about 25 kilojoules per mole. So at room temperature, the enantiomers constantly interconvert, resulting in a racemic mixture. You can't isolate one form.
That's pretty neat. What about more basic properties like solubility and boiling point?
Solubility follows typical trends. Amines with fewer than, say, 5 carbon atoms can hydrogen bond effectively with water, so they tend to be water-soluble. As the carbon chain gets longer and more hydrophobic, solubility decreases.
Makes sense. And boiling points.
Primary and secondary amines, those with NH bonds, can form hydrogen bonds with each other. This intermolecular attraction means they have higher boiling points than comparable alkanes of similar molecular weight.
But lower than alcohols, right?
Lower than alcohols, yes. Because nitrogen is less electronegative than oxygen, the NH hydrogen bonds are weaker than OH hydrogen bonds.
And is there a trend among amines themselves? Like primary versus secondary versus tertiary?
Definitely. Primary amines with 2 NH bonds can hydrogen bond more extensively than secondary amines, which have only 1 NH bond. Tertiary amines have no NH bonds, so they can't hydrogen bond with each other at all.
So the boiling point trend is primary, secondary, tertiary, generally.
Exactly. For example, propylamine, 1 degree, boils around 50 degrees, ethylmethylamine, 2 degrees, around 34 degrees C, and trimethylamine, 3 degrees, boils way down at 3 degrees C. It clearly shows the impact of hydrogen bonding capacity.
And we mentioned odors earlier, putrescine, but generally.
Yeah, low molecular weight amines often have a characteristic fish-like odor. That smell of fish. It's largely due to amines produced as proteins break down.
Okay, let's get to what you said is maybe their defining characteristic, basicity.
Right. Amines are generally stronger bases than related compounds like alcohols or ethers. They readily accept a proton, even from relatively weak acids like acetic acid.
How do we quantify that? How do we compare the basicity of different amines?
We measure it using the pico value of their corresponding conjugate acid, the ammonium ion formed when the alene accepts a proton.
Okay, wait. The pico of the acid tells us about the strength of the base. How does that work?
It can seem backward at first, but think about the equilibrium. Amine plus H plus a ammonium ion.
Mm.
A high pico for the ammonium ion means it's a weak acid, meaning it doesn't like to give up its proton.
So if the ammonium ion holds onto its proton tightly.
It means the original amine was good at accepting that proton in the first place. It's a strong base. So high pico of the conjugate acid is strong amine base.
Got it. High pico ammonium, strong base. Ammoniamine, is that useful practically?
Incredibly useful. It's the basis for solvent extraction to purify amines. If you have a mixture of an amine and some neutral organic compounds in an organic solvent, you can add aqueous acid.
The amine gets protonated.
Exactly. It
Yeah.
becomes a charged ammonium ion, which is now water-soluble. So you shake the layers, and the ammonium ion moves into the aqueous layer, leaving the neutral stuff behind in the organic layer. Separate the layers, then add base back to the aqueous layer to neutralize the ammonium ion and regenerate your pure amine.
Clever. That's how they originally isolated alkaloids from plants.
That's right. They exploited this difference in basicity, hence the name alkaloid, meaning alkali-like or basic.
Does the structure of the amine affect its basicity much?
Hugely. A major factor is whether the amine is alkyl or aryl. Aryl amines, like aniline, are significantly less basic than typical alkylamines.
Why is that?
Resonance. The lone pair on the nitrogen in aniline isn't just sitting there. It's delocalized, spread out into the aromatic ring through resonance structures.
Okay.
If aniline accepts a proton, the delocalization is lost. The resulting aniline ion is less stable because it loses that resonance stabilization. So aniline is less willing to accept a proton. It's a weaker base.
And what about substituents on the aromatic ring? Do they matter?
They do. Electron-donating groups, like a methoxy group, can slightly increase basicity by pushing electron density towards the nitrogen. But electron-withdrawing groups, like a nitro group, dramatically decrease basicity.
Why so dramatic?
Because they pull electron density away from the nitrogen and can participate in resonance that further delocalizes the lone pair, making it even less available for protonation. Paranitranline is a very weak base because of this extensive delocalization.
What about amides? They have nitrogen next to a carbonyl.
Amides are an extreme case. That nitrogen lone pair is heavily involved in resonance with the adjacent carbonyl group, CNO. This makes the lone pair almost completely unavailable. Amides are essentially non-basic and also poor nucleophiles because of this strong resonance effect.
Okay, so delocalization is key. How does this play out in nitrogen heterocycles, those ring structures, like pyrrole versus pyridine?
Great comparison. Both are aromatic rings containing nitrogen. In pyrrole, a 5-membered ring, the nitrogen's lone pair is part of the 6 pi electrons needed for aromaticity, according to Huckel's rule.
So if pyrrole gets protonated,
It loses its aromaticity. That's a huge stability loss. Consequently, pyrrole is an incredibly weak base. Its lone pair is tied up maintaining that aromatic system.
but pyridine, the 6-membered ring.
In pyridine, the nitrogen's lone pair sits in an sp2 orbital outside the aromatic pi system. The 6 pi electrons for aromaticity come from the carbons and 1 from the nitrogen's p orbital. That external lone pair is available for protonation without disrupting aromaticity.
So pyridine is a stronger base than pyrrole.
Much stronger than pyrrole, yes, but it's still weaker than typical alkylamines.
Why weaker than alkalines?
Because the lone pair in pyridine is in an sp2 orbital, which has more Se character than an sp3 orbital. More Se means the electrons are held closer and more tightly to the nucleus, making them less available, hence slightly less basic.
This basicity has real biological implications too, right?
Oh, yeah.
Especially at physiological pH.
Absolutely critical. Physiological pH is around 7.4. Most common alkylamines have conjugate acid pKa values around 911. This means at pH 7.4, they exist predominantly in their protonated charged ammonium form. This charge affects how they interact with cell membranes, receptors, enzymes, everything. Understanding this is vital for drug design.
And you mentioned a wild example earlier, ants.
Yes, and chemical warfare. It's fascinating. Fire ants inject a neurotoxin called solanopsin, which is a cyclic amine. It's hydrophobic, designed to penetrate the victim's cuticle and nervous system.
The nasty stuff.
But tawny crazy ants have this amazing defense. They secrete formic acid, the simplest carboxylic acid, and basically bathe themselves in it.
They cover themselves in acid.
Yeah. So when a fire ant injects solanopsin, the formic acid on the crazy ant's body immediately protonates the solanopsin amine.
Turning it into the ammonium salt.
Exactly, an ionic salt. Now it's charged and no longer hydrophobic. It can't penetrate the crazy ant's waxy hydrophobic cuticle. The formic acid effectively neutralizes the toxin using simple acid-base chemistry. Isn't that amazing?
That is truly incredible. Chemistry in action in the insect world. Okay, so we understand what amines are and their properties. How do chemists actually make them?
There are several ways. We've encountered some methods in earlier chemistry. For instance, you can start with an alkyl halide, react it with cyanide ion via SM2 to form a nitrile, which adds one carbon.
And then reduce the nitrile group, often with lithium aluminum hydride, LiLH4, to get a primary amine.
Right. Or you could start with a carboxylic acid, convert it to an amine using, say, thionyl chloride, then ammonia.
And then reduce that amide again, often with LiLH4, to get an amine with the same number of carbons as the original acid.
Correct. And for making aromatic amines, like aniline from benzene, a standard route is nitration of benzene using nitric and sulfuric acid to get nitrobenzene.
Followed by reduction of the nitro group. You can use metals like iron, tin, or zinc in acid, or catalytic hydrogenation, HDPT.
An important note there. If you use acidic conditions for the reduction, the amine product will be protonated. You often need to add a base afterwards to get the neutral amine. Selective reducing agents are also useful here.
Okay, those are review methods. What about newer preparations, maybe focusing on substitution reactions? Can't you just react ammonia with an alkyl halide?
You can. Via an SN2 reaction, ammonia acts as the nucleophile. But there's a big practical problem. Polyalkylation.
Meaning?
The primary amine product you form is actually more nucleophilic than the starting ammonia. So it can react with another molecule of alkyl halide to form a secondary amine.
And that secondary amine is still nucleophilic.
So it reacts again to form a tertiary amine. And that can react again to form a quaternary ammonium salt if you have enough alkyl halide. You end up with a messy mixture.
So direct alkylation of ammonia isn't very clean for making primary amines.
Generally not, unless the alkyl halide is super cheap and you don't mind a mixture, or if you specifically want to make the quaternary ammonium salt by using excess alkyl halide, exhaustive alkylation.
So what are better ways to get pure primary amines via substitution?
Two key methods. First is the azide synthesis. You react an alkyl halide with sodium azide, NN3, in an SN2 reaction to form an alkylazide. Azide ion N3 is a good nucleophile.
Okay, an alkylazide. Then what?
Then you reduce the azide group, usually with LiLH4, and that cleanly gives you the primary amine. It avoids polyalkylation because azide isn't nucleophilic enough to react further.
Any downsides?
The main one is safety. Alkylazides, especially low molecular weight ones, can be explosive. You have to handle them carefully.
Right. What's the other main method for pure primary amines?
The Gabriel synthesis. This is often the preferred method, especially for primary alkyl halides. It uses potassium phthalimide as the nucleophile.
Phthalimide, what's that?
It's a molecule with an NH group sandwiched between two carbonyl groups. That makes the NH proton quite acidic, so you can easily deprotonate it with a base like potassium hydroxide to form the phthalimide anion.
And that anion is the nucleophile.
Yes, potassium phthalimide. It reacts cleanly with a primary alkyl halide via SN2. The bulkiness of the phthalimide group prevents overalkylation.
So you get N-alkylated phthalimide. How do you get the amine out?
You then hydrolyze the N-alkyl phthalimide, typically using strong acid, strong base, or, more commonly, hydrazine, H2 and NH2. This cleaves the bonds and releases the pure primary amine, leaving behind a phthalihydrazide byproduct. It's a very reliable way to make primary amines.
Okay, azide and Gabriel for primary amines. What about making secondary or tertiary amines cleanly, or just a more versatile method overall?
For that, reductive amination is incredibly powerful and versatile.
Reductive amination, what's the core idea?
You start with a ketone or an aldehyde. You react it with ammonia or an amine under slightly acidic conditions. This forms an intermediate called an amine, if from ammonia, or a primary amine, or an aminium ion, if from a secondary amine.
Like replacing the CO octanol with the CN nitrogen.
Essentially, yes. And the key is, you don't isolate that aminium ion. You immediately add a reducing agent in the same pot that reduces the C and N double bond, or CSN plus bond, to a CN single bond.
Ah, so you form the CN bond and reduce it right away. What kind of reducing agent? Can you use LiLH4 or an ABH4?
You could, but they might also reduce your starting ketone or aldehyde, which you don't want. A much better choice is a milder, more selective reducing agent, like sodium cyanobrohydride, MEBH3CN.
Why is that one special?
MEBH3CN is clever. It's not strong enough to reduce the ketone or aldehyde itself under the reaction conditions, but it is strong enough to reduce the protonated aminium ion intermediate as it forms. It selectively targets the CN plus bond.
So it waits for the aminium to form and then reduces only that?
Exactly. It allows the whole transformation from carbonyl to amine to happen efficiently, often in one step.
And you said it's versatile.
Hugely. If you use ammonia, NH3 with your ketonealdehyde, you form a primary amine. If you use a primary amine, RNH2, you form a secondary amine, R2NH. If you use a secondary amine, R2NH, you form a tertiary amine, R3N. You can build complexity easily.
The chapter shows how fluoxetine, Prozac, can be made using this method. You can think backwards about which CN bond to form.
Right, that retrosynthetic thinking is key. Reductive amination offers multiple ways to construct the target CN bond, depending on the available starting materials.
So, summing up synthesis strategies. For pure primary amines, Gabriel or maybe a DAFED synthesis are good choices.
Yes, for secondary or tertiary amines, reductive amination is usually much better than trying direct alkylation of a lower amine because you avoid the polyalkylation best.
And if you actually want a quaternary ammonium salt,
Then direct exhaustive alkylation of the tertiary amine with excess alcohol is the way to go. It's efficient for that specific product.
okay, we know how to make them. What about their reactions? What do amines do? A key one seems to be acylation.
Right. Amines, acting as nucleophiles, readily react with acyl halides, or acid anhydrides, to form amides. This is a standard nucleophilic acyl substitution reaction.
You usually need two equivalents of the ivrilene, though, right?
Good point. Yes, one equivalent acts as the nucleophile, attacking the carbonyl carbon. The reaction releases HCl, if using an acyl chloride, and the second equivalent of amine acts as a base to neutralize that acid. Otherwise, the acid would protonate your starting amine, making it non-nucleophilic.
This acylation to form an amide has a really important strategic use, doesn't it? Especially in aromatic chemistry.
Absolutely. It's a brilliant protecting group strategy, particularly for aniline and its derivatives during electrophilic aromatic substitution, EAS.
What's the problem with doing EAS directly on aniline?
The amino group, NH2, is a very strong activating group. If you try to, say, brominate aniline, you don't just get one bromine add, you get tribromination almost instantly because the ring is so reactive it's hard to control.
And there's another issue with Friedel-Crafts reactions.
Yes. Friedel-Crafts reactions require a Lewis acid catalyst, like LCl3. But the nitrogen lone pair in aniline is basic enough to react with the Lewis acid, forming a complex. This deactivates the nitrogen, making it strongly deactivating towards EAS, shutting down the Friedel-Crafts reaction.
So the solution?
Protect the amine first. React aniline with something like acetic anhydride to form acetanilide, an amamide.
How does that help?
The resulting amamide group, NHCOCH3, is still activating and orthopair directing for EAS, but much less strongly activating than the original amino group. This allows you to achieve controlled reactions, like monobromination.
Ah, you tame the reactivity and the Friedel-Crafts problem.
Solve 2. The amide nitrogen's lone pair is tied up in resonance with the carbonyl, remember? It's no longer basic or nucleophilic enough to interfere with the Lewis acid catalyst. So you can perform Friedel-Crafts reactions on the protected aniline derivative.
And then afterwards, you just remove the protecting group?
Exactly. Yeah. After you've done your desired EAS reactions, you simply hydrolyze the amide back to the amine using aqueous acid or base. It's a fantastic strategy for controlling reactivity and enabling reactions that wouldn't work otherwise.
Very clever. Okay, another reaction mentioned is the Hofmann elimination. What's that for?
The Hofmann elimination is a way to convert an amine into an alkene. It's an elimination reaction, but with a twist.
How does it work?
It's a two-step process. First, you treat the amine with excess methyl iodide, CH3I. This is called exhaustive alkylation. It converts the amine all the way to the quaternary ammonium iodide salt.
Why do that?
It turns the nitrogen group into a really good leaving group. The neutral trialkylamine molecule that leaves is stable.
Okay, step 1. Make the quaternary ammonium salt. Step 2.
Step 2 is the elimination itself. You treat the quaternary ammonium salt with a strong base, typically generated by using aqueous silver oxide, Ag2O. The silver oxide swaps the iodide cantarian for hydroxide, OH, which then acts as the base to promote an E2 elimination reaction, kicking out the trialkylamine leaving group and forming an alkene.
Standard E2 elimination, so it should favor the more substituted alkene, the Zaitsev product, right?
Ah, that's the twist. Hofmann elimination typically favors the formation of the less substituted alkene. This is often called the Hofmann product as opposed to the Zaitsev product.
Why the opposite regiochemistry for most E2 reactions?
It mainly comes down to sterics. The leaving group, the quaternary ammonium group in NR3+, is very bulky. For the E2 reaction to occur, the base needs to abstract a proton antiparaplanar to this bulky leaving group. Accessing the proton that would lead to the more substituted sites of alkene often involves a more sterically hindered transition state due to gauche interactions with the bulky leaving group. Removing a proton from the less substituted carbon, leading to the Hofmann product, is sterically easier and therefore faster. It's under kinetic control.
So the bulkiness of the leaving group dictates the outcome, favoring the less substituted Hofmann product. Interesting.
It is. It provides a way to selectively form less substituted alkenes, which can be synthetically useful.
Next step, reactions with nitrous acid, HNO2. You mentioned this is made in situ.
Yes, nitrous acid is unstable, so you always prepare it fresh right in the reaction flask, usually by mixing sodium nitrite, NNO2, with a strong aqueous acid like HCl or H2SO4. This generates the active electrophile, the nitrosonium ion NO plus SEZA.
What happens when amines react with this nitrosonium ion? Does it depend on the anion type?
It does, significantly.
Yeah.
Secondary amines, R2NH, react with the nitrosonium ion to form N-nitrosamines, which have an NNO group.
And nitrosamines, aren't those bad?
Yes, many N-nitrosamines are known to be potent carcinogens. This is a concern, for example, with nitrites used in curing meats, as they can potentially react with amines present in proteins under acidic stomach conditions.
Yikes. Okay, what about primary amines?
Primary amines, RNH2, react differently. They undergo a process called diazotization to form diazonium salts, which have an Rn2 plus structure.
Diazonium salts, are they useful?
It depends. If you start with a primary alkylamine, the resulting alkyl diazonium salt Rn2 plus is extremely unstable. It spontaneously decomposes, rapidly releasing nitrogen gas and N2, which is a fantastic leaving group, to form a carbocation.
Carbocations often lead to messy mixtures of products, right? Rearrangements, substitutions, eliminations.
Exactly. Alkyl diazonium salts decompose uncontrollably, sometimes explosively, and give complex mixtures. They're generally not synthetically useful.
But you emphasized alkyl. What about aryl primary amines, like aniline?
Ah, that's where it gets incredibly interesting and useful. When you diazotize a primary arylamine, you form an aryl diazonium salt, ARN2+. And crucially, these are much more stable than their alkyl counterparts, especially at low temperatures, around D-aroused 5 degrees C.
Why are they more stable?
Because the alternative, forming a highly unstable aryl cation by losing N2, is energetically very unfavorable. So aryl diazonium salts hang around long enough for us to use them.
And use them you do. The chapter calls them a synthetic Swiss Army knife.
That's a perfect description. Aryl diazonium salts are amazingly versatile synthetic intermediates. The diazonium group, Natchez N2+, is an excellent leaving group, and it can be replaced by a wide variety of other functional groups, many of which are difficult to introduce directly onto an aromatic ring via other methods.
Like what kind of replacements can you do?
Well, there are the Sandmeyer reactions, which use copper I salts as catalysts. With copper I bromide, 2-mer, you replace Natchez N2+ with MaCuSDr. With copper I chloride, CQCl, you get the diCCl. With copper I cyanide, QTCN, you get a cyano group, NetGCN.
And that cyano group is useful too, right? You can hydrolyze it.
Exactly. Hydrolyzing the NECN group gives you a carboxylic acid, DCOH. So diazotization followed by Sandmeyer with QCN, and then hydrolysis is a two-step way to put a carboxylic acid group onto an aromatic ring, starting from an amino group.
Very neat. What about other halogens? Fluorine.
Fluorine is notoriously difficult to add directly to aromatic rings, but you can make an aryl fluoride from a diazonium salt using the Hofmann reaction. You treat the diazonium salt with fluoroboric acid, HBF4, which precipitates the diazonium tetrafluoroborate salt. Gently heating this salt causes it to decompose, replacing the NegaSN2 plus group with fluorine, DSWA.
Wow. Okay, so halogens, cyano group. What else?
You can replace the diazonium group with a hydroxyl group, HH, essentially making a phenol simply by heating the aqueous solution of the diazonium salt.
Water acts as the nucleophile.
Right. And another really powerful transformation is replacing the diazonium group with just a hydrogen atom. You treat the diazonium salt with hypophosphorus acid, H3PO2.
Why would you want to go to all the trouble of putting an amino group on, converting it to a diazonium group, just to remove it and replace it with hydrogen?
It's all about controlling regiochemistry in multi-step syntheses. The amino group is a strong orthopara director. You can use its directing influence to install other substituents at specific positions, and then remove the amino group via diazotization and reduction with H3PO2 when it's no longer needed. For example, making 1,335-tribromobenzene is tricky directly, but you can start with aniline, tribrominate it, easy because managed NH2 is activating, then remove the amino group via this method.
Using the amine as a temporary steering group, that's clever strategy.
It's incredibly useful. And there's one more major reaction of aryl diazonium salts.
Mesocoupling.
Mesocoupling. Sounds colorful.
It is. Aryl diazonium salts are electrophilic enough to react with highly activated aromatic rings that have strong electron-donating groups like NLH, phenols, or NR2, anilines. This is an electrophilic aromatic substitution reaction where the diazonium ion is the electrophile.
And the product? The product is an azo compound, which contains an NEN double bond, the azo group, linking two aromatic rings. These compounds are typically highly conjugated systems.
And high conjugation often means
Color. Azo compounds form the basis of a huge class of synthetic azo dyes, responsible for vibrant colors in everything from textiles to food coloring to laboratory indicators. It's beautiful chemistry with very practical applications.
amazing versatility from those diazonium salts. Okay, let's shift slightly to nitrogen heterocycles, rings with nitrogen in them.
Right. A heterocycle is just a ring containing atoms of more than one element. Nitrogen heterocycles are incredibly common in nature and in pharmaceuticals. Think Viagra, Nexium. Lots of blockbuster drugs feature these rings.
The chapter focuses on a few key examples, starting with five-membered rings like pyrrole and imidazole. We touched on pyrrole's basicity earlier.
Yes, pyrrole's nitrogen lone pair is part of its aromatic system, making it a very weak base and not very nucleophilic. It does undergo electrophilic aromatic substitution, primarily at the C2 position because the intermediate is more stable.
And imidazole, it's similar but has a second nitrogen.
Correct. Imidazole also has a five-membered aromatic ring, but with two nitrogen atoms. One nitrogen is like pyrroles, its lone pair is part of the aromatic system, but the other nitrogen is like pyridines. Its lone pair is in an sp2 orbital outside the pi system.
So that second nitrogen makes imidazole more basic than pyrrole.
Yes, it's significantly more basic, though still less basic than alkylamines. Imidazole is a really important heterocycle. Biologically, it's the core structure in the amino acid histidine and in histamine.
Histamine. That brings us back to stomach acid and that cimetidine tegamet story.
It does. It's a landmark case study in medicinal chemistry. The problem was histamine stimulates stomach acid secretion by binding to specific receptors called H2 receptors. Traditional antihistamines, like Benadryl, only blocked H1 receptors, involved in allergies, not H2 receptors.
So researchers needed something that looked like histamine but would block, not activate, the H2 receptor, an antagonist.
Exactly. Sir James Black led the effort. They started making compounds structurally similar to histamine, but modified them systematically. It was a long process. They made compounds like N-guanylistamine, which was only a partial agonist. It blocked a bit, but also stimulated a bit. Not good enough.
How did they improve it?
Key insights involved adjusting the electronic properties and basicity, pK, of the imidazole ring by adding different groups and lengthening the side chain connecting the ring to the terminal nitrogen group. They also use a technique called isosteric replacement.
Isosteric replacement.
That means replacing an atom or group with another atom or group that has a similar size and shape but different electronic properties. For example, they replaced a CH2 group in the side chain with a sulfur atom, S. This maintained the overall shape needed to bind the receptor but altered the electronic properties, leading to better antagonists like burimamide.
Was burimamide the answer?
Almost. It was an antagonist, but its activity wasn't great when taken orally. More modifications led to metimide, which was potent, but unfortunately caused some side effects, loss of white blood cells, due to its thiourea group.
So one final tweak needed.
Yes. They replaced the problematic thiourea group with a cyanoguanidine group, which has similar electronic properties, but crucially, isn't significantly protonated at physiological pH. This final modification yielded cimetidine tegamet.
And it was a huge success.
Revolutionary. The first drug ever to reach over $1 billion in annual sales, a true blockbuster. It transformed the treatment of ulcers and acid reflux and paved the way for later H2 antagonists like ranitidine, Zantac, and famotidine, Pepcid, a triumph of rational drug design based on understanding structure, basicity, and receptor interactions.
Amazing story. What about the six-membered heterocycles? Pyridine and pyrimidine.
We already discussed pyridine's basicity stronger than pyrrole because its lone pair is localized outside the aromatic pi system, but weaker than alkylamines due to this sp2 hybridization.
Does pyridine undergo electrophilic aromatic substitution?
It does, but it's much less reactive than benzene. The nitrogen atom acts as an electron-withdrawing group via induction, deactivating the ring towards electrophilic attack. Reactions usually require harsh conditions, high temperatures, and substitution occurs primarily at the C3 position.
And pyrimidine, like pyridine but with a second nitrogen?
Yes, at position 3. This makes it even more electron deficient and less basic than pyridine. Pyrimidine rings are fundamental components of nucleic acids, Thymine, cytosine, and uracil are all pyrimidine derivatives found in DNA and RNA.
Okay, one last area. How do chemists actually identify amines using spectroscopy? What are the telltale signs?
Spectroscopy gives us molecular fingerprints. In infrared, IR spectroscopy, the key is the NH bond stretch. Primary amines, RNH2, show two characteristic peaks in the 3,350-3,500 centimeter 1 region due to symmetric and asymmetric stretching.
2 peaks for primary. What about secondary?
Secondary amines, R2 and H, have only one NH bond, so they show only one peak in that same region.
And tertiary amines, R3N.
Tertiary amines have no NH bond, so they show no signal in that region. The absence of a signal there in a compound known to contain nitrogen is good evidence for a tertiary amine. You can sometimes see the NH stretch of its protonated ammonium salt form if you treat it with acid, but that's further down around 2,200, 3,000 centimeters 1.
Okay, IR gives clues based on NH bonds. What about NMR spectroscopy? Proton 1H, NMR first.
In 1H NMR, the protons directly attached to the nitrogen, NH protons, usually show up as a broad signal somewhere between 0.5 and 5.0 ppm. The exact position can vary a lot.
Why broad, and why the variable position?
They're broad due to hydrogen bonding and also because of quadrupolar relaxation from the nitrogen nucleus. Their position varies because it's sensitive to concentration, solvent, temperature. Also, these NH protons are labile. They exchange rapidly with acidic protons in the solvent, like trace water, or with each other, which usually averages out any coupling, so you typically don't see splitting for the NH proton itself.
And they exchange. Can you use that?
Yes. If you add a drop of deuterium oxide, D2O, to your NMR sample and rerun the spectrum, the NH protons will exchange with deuterium, Nd, and the NH signal will disappear. It's a classic test for exchangeable protons like those in OH or NH groups.
What about protons near the nitrogen, on the carbons?
Protons on the carbon atom directly attached to the nitrogen arcane. The alpha protons are de-shielded by the electronegative nitrogen. They typically appear in the 2-3 ppm region, shifted downfield compared to protons in a simple alkane. This effect decreases with distance from the nitrogen.
Okay. And carbon-13, 13C, NMR.
Similar effect. The carbon atom directly bonded to the nitrogen, the alpha carbon, is also de-shielded. It typically appears in the 30-50 ppm range, the 13C spectrum, which is about 20 ppm or so downfield from where a similar carbon in an alkane would appear. Again, the effect tapers off with distance.
Finally, mass spectrometry. Any unique clues for amines?
Two main things. First, the nitrogen rule. It states that a compound containing an odd number of nitrogen atoms will have a molecular ion, M+, with an odd molecular weight. If it have an even number of nitrogens, or 0, the molecular weight will be even. It's a quick check.
Odd number of nitrogens equals odd molecular weight. Got it. Second clue.
Amines undergo a very characteristic fragmentation pattern called alpha cleavage. The molecule tends to break at the bond between the alpha carbon and the atom next to it, beta carbon. This happens because the resulting fragment, an ammonium ion, is resonance stabilized. Seeing fragment ions resulting from alpha cleavage is strong evidence for the presence of an amine.
Wow. Okay, that was a really comprehensive dive into amines. We've covered their basic structure, naming, properties like basicity and inversion.
The key methods for making them, like Gabriel synthesis and especially reductive amination.
And they're really important reactions: acylation for protection, Hofmann elimination giving the less substituted alkene, and those incredibly versatile diazonium salt reactions for synthesis and dyes.
Exactly. From understanding how tagamet works, to the chemical defenses of ants, to building complex molecules in the lab, amines are just fundamental.
They really are everywhere, performing such a wide range of vital functions in chemistry, biology, and medicine.
It makes you think, doesn't it, about all the intricate chemical processes happening constantly, all around us and inside us.
Absolutely. As you go about your day now, maybe you'll consider that hidden chemical dance. How might understanding these principles of organic chemistry help you see the world differently, or maybe even spark your own next great idea?
Thank you for joining us on this deep dive. We really appreciate you being part of our last-minute lecture family.
Yeah, thanks everyone. Keep learning, keep questioning, and until next time, stay curious.